Good morning, everyone. It's my pleasure to be here, and a particular pleasure to introduce to you William Baker. Maybe some of you have been traveling to Dubai, and already when you fly in, you see this remarkably elegant high tower, the Burj Khalifa, the highest building in the world. Maybe you even got a ticket to get up there. It's a bit shaky, actually. But today, we have the chief engineer of this building here, Bill Baker. He is a celebrated structural engineer who received numerous awards, including 2 honorary doctorates. He's a member of the National Academy of Engineering in the US, of the Royal Academy of Engineering in the UK. And I admire him particularly because in his free time, he is still doing research. So this is quite amazing. He also has a group doing some research with him at SOM. And what is a particular pleasure for me that this research is even related to geometry. And if you look at his title, on the harmony of structure, architecture and geometry, what would be a better fit for this event today? So it is my pure pleasure to ask Bill to give his presentation. We are very honored that you are here today.
Thank you very much for that introduction, and thank you for inviting me to be here. You may not realize it, but this is one of the world centers, and maybe the center of architectural geometry. It comes out of the work here in Vienna. Anyway, so I want to talk about the harmony of structure, architecture, and geometry. But first, I want to talk a little bit about something that's about architects, engineers, and geometers, okay? And particularly something called the street light effect. I don't know if you've seen, there's cartoons like this. Here's this man on the ground under a street light. And the policeman says, "Is this where you lost your wallet?" "No, I lost it in the park, but this is where the light is." And in general, what happens is we have a problem. We don't necessarily address the problem. We address what we know to do. We go under our street lamp and explore when perhaps there's, the problem is elsewhere. And what's interesting is that architects and engineers and geometers have different street lamps. And so, here's another cartoon. I'm looking for my quarter I dropped. Did you drop it here? No, I dropped it 2 blocks down the street. Why are you looking for it here? Because the light is better here. And so the architects, engineers, and geometers have different street lights. And I wish I could see what you guys see, and I want you to see what I see. And somehow can we get these knowledge bases closer to each other? Now, let me talk about structure and architecture. In fact, this room, you could not describe this room. If someone asked you to describe the architecture, you would describe the structure. If someone asked you to describe the structure of this room, you would have described the architecture. They're inseparable. And it's like a Mobius strip, another geometric form. You start on one side and you end up on the other. Architecture, structure, one would hope that they would go together. They don't always do, but one would hope they would do. The building that I showed earlier, you cannot describe the structure without describing the architecture. They're integral. There's a building I did a long time ago in London. If you ever go take a train out of Liverpool Street Station going up to Cambridge, you go under this building. It's a building that's a bridge because it's going over a train yard that's underneath. Now, architecture is a story of a place and time, like this room we're in right now, or the chapel at King's College in Cambridge. But so architecture tells the story of a time and place, but structure forms the words of the story. Here it's the flying buttresses, or this incredible vault, this fan vault that's in the chapel, that's held together by geometry. There is no reinforcement, there's no rebar, this is all just stone. The only reason it does not fall down is that it has the right geometry. And in some places it's only 100 millimeters thick. held together by geometry and gravity. And I challenge most structural engineers today to be able to design this that was done 500 years ago, because we don't know enough about geometry. And then you look at recent architecture. I travel the world. I go to Dubai or Shanghai or places, London, places around the world, and I see a bunch of buildings that, for me, here you have the KPF bottle opener next to an SOM pagoda, next to something that's supposed to be a dragon, next to a shish kebab. And I look at that, I said, have we run out of good ideas? They remind me of the movie Brazil. And Ida Lowry, I urge you all to watch the movie Brazil. And this architecture reminds me of Ida Lowry's hat. She has this shoe hat. And so can we create new architecture that's not about putting a silly hat on a building? All these buildings are saying, look at me. Like this woman was walking down the street, you would notice her. But then maybe not. When all the buildings shout, look at me, you see none of them. It's like you're in a crowded restaurant and everyone's shouting and you can hear no one because everyone's drowning out each other with their silly hats and the like. So the challenge is to create ideas and technology that will lead to new architecture, but it's new architecture that is substantive, that it looks different because it's actually better. And that's what our goal is. And to me, geometry is absolutely the key to this. Why does geometry matter? We talked about the architectural part of geometry. But from my world as I'm a structural engineer in an architectural firm. Skidmore & Merrill is a firm of primarily architects and some engineers. And we do buildings such as this building here, the Hancock in Chicago. And structural systems are essential not only to the architecture, but to the efficiency. And geometry is absolutely critical to structural systems. Here are two trusses that do exactly the same job, truss A and truss B. The truss A is what we might call the moment diagram. The truss B is might call a Warren truss. The one on the left, for same equal stresses, the one on the left needs 27% more material than the one on the right. For deflection, it needs 60% more material. Not 6%, not 16%, 60%. Talk about carbon, embodied carbon, and the difference between the two is geometry. Now, we're in the middle of this terrible climate crisis, and everything we build today it delivers carbon to the atmosphere now. And a new building is the embodied carbon is primarily structure. If you count the substructure and the superstructure, it's way up there, almost two-thirds, close to two-thirds of the carbon on a building in day one comes from structure. So we should get some very, very efficient structures when we build new buildings. Okay, I'm going to use a little terminology. In the office, as Helmut says, we have our research group. And our research group is not a standalone research group. They are all people, architects and engineers, who work on projects as their day job. And then, and after hours, we then think about things we don't know and do research. And it's so much more efficient to have the research done by people who are actually working on projects, because they will find applications that you never imagined. Most of our research is totally blue sky. We generally do not have any idea what we're going to do with the knowledge we're looking for, but we will find applications because we are designers. And one of the things that happened early on is we would talk to each other and we didn't understand because we were using the same word to mean different things. So I'm going to give a little terminology that we use in the office, and it may not be right for you guys, but okay. But here goes. We have the terminology I'm going to use in this talk is we have something called the domain, the design domain where structure might exist, that gray rectangle. And then we have topology. By that we mean who is connected to whom. So these two geometries, these two layouts they do the same job, but they have different topologies. Okay? The next term we like to use is shape. Both of these have the same topology, but different shapes. And then finally, down here is size. What is the size of the individual elements or the connections and the like? You know that structure I showed you just a minute ago, the A and B? I don't care how good you're going to be at sizing the member or the connections, you cannot get beyond a bad geometry. And so the most important parameters are topology and shape, which is architecture. So the architects and geometers need to be involved in the creation of topology and shape. And over time, structural technology leads to new architecture. So can we do what people have done in the past? If you go back to the Mayans, they had a very limited structural technology. They had the corbel arch. Well, guess what? Their architecture was pretty limited. The Greeks had a very limited vocabulary. They did really well with just a beam and post, a pretty remarkable architecture for a very limited vocabulary. The Romans, of course, brought in a richer structural vocabulary in the form of arches and domes, which created the opportunities for new and better architecture. The Gothic era was a highlight period of structure and architecture and geometry coming together. The thrust of that building has to be in the masonry, or the masonry would fall down. It cannot be anywhere else. Now you go into the beginning of the modern era when metals came along, and you have like the work of Thomas Telford in the early 19th century, or Brunel towards the middle of the 19th century, or going back towards the end of that 19th century, the work of Guastavino and others who created these incredible vaults that are just purely very efficient compression structures created by their own geometry. If you ever go to New York City and you eat in the Oyster Bar under Grand Central Station, you will be eating under a Guastavino vault. That vault is the structure. It's holding up the train hall above it. Okay? Go back 100 years, Vladimir Sukhov, an incredibly brilliant engineer who created many wonderful structures. The GUM department store skylight is a Sukhov thing. Or these hyperboloid towers, such as the Moscow Tower, were created 100 years ago now by Vladimir Sukhov. And so, he brought this new geometry to architecture. The work of Robert Maillard, who's not only the geometry of his structure, but the geometry of his forces. He designed the forces at the same time he was designing the structure through something called graphic statics, which I'll talk about in just a moment here. Or Torroja with his concrete shells, or Pierluigi Nervi with this incredible sports facility with the dome, and then these essentially these concrete people who are holding up the dome. You can see the front leg and their back leg and their two arms going up in a circle to hold up the dome of this. Or Felix Candela, who did amazing things with a very limited vocabulary of hyperbolic paraboloids. That's incredible. Look how beautiful and slender that is from this hyperbolic paraboloid. Or Bucky Fuller with his geodesic domes. Heinz Eisler with his free-form shell structures formed by hanging burlap and hanging fabric and seeing what the shape is. Or Diesta, this is a bus terminal in Uruguay. It's brick. That is brick that he post-tensioned together. Quite remarkable. Of course, the work of Frei Otto with his research up down in Stuttgart, with soap films and, and other materials that led to the incredible new architecture of the Olympic Stadium or the Mannheim Multihalle in Mannheim. Incredible structures. Here's an artist that I work with quite a bit now. Her name is Janet Eckelman, and this is an art piece we did in West Hollywood, California. And you look at that geometry, and even more so than the masonry, where is the force? It has to be in the rope. And for every node there that you see with your eyes of the ropes coming together, there's an invisible but equally real a polygon of forces that are closing for it to be in equilibrium. And so that brings me to the geometry of equilibrium, a very, very important topic, which is all of these things I've showed you are based on the geometry of equilibrium. And a very important contributor to this conversation was James Clerk Maxwell. Now, Maxwell is most famous for his work in electromagnetic theory. When Einstein first went to England, they asked him, did you stand on the shoulders of Newton? He said, no, I stood on the shoulders of Maxwell. Maxwell's work led to that. But he also did some very important work in engineering mechanics, or essentially structural engineering. And he's responsible for something called reciprocal figures and graphic statics. Here is his paper from 1864. The title is On Reciprocal Figures and Diagrams of Forces, Geometry. Okay? And he talks about what is a reciprocal figure. A reciprocal figure are such that the properties of the first relative to the second are the same as those of the second relative to the first. Okay, now we're going to get into the stuff that I had no idea what he was saying initially. Thus, inverse figures and polar reciprocals are instances of two different kinds of reciprocity. I had no idea what a polar reciprocal was when I first read this. And here we are. So here is a structure on the left, looks like a truss. The red arrows are the forces, the black elements of the structure. And here's the geometry of the structure. Well, here is the geometry of the forces. And every bar on the left has a parallel bar on the right. So the polygons here are polygons 1, 2, 3, 4, 5, 6. And then between the exterior forces, we call these open polygons, A, B, C, D, E. So the force in member C4 is the length from, where's C to 4. The length of that line is the force in that bar. And what happens is that every polygon here maps to a node, and every node maps to a polygon. So if I go B, C, 4, 3, B, if I go B, C, 4, 3, B, that polygon maps to that force. So these are reciprocal figures. The mapping of one, so a polygon maps to a point maps to a polygon. Each figure has the same number of lines, and every line here has a line over there that is parallel. So 2, 3. So this line is parallel, 2, 3. So these are reciprocal figures. And this is graphic statics. And you can imagine, and this was how people used to do calculations for trusses, they do it graphically. And you can imagine that you could really get a figure, a feeling for how big the forces are when you drew that line. As opposed to, nowadays we have these computer programs, and the computer will give you like a blue-green color. I have no idea what to do with that. Okay, I design structures all over the world, but when an engineer brings to me this finite element program, I'm trying to interpret what does blue-green mean, it's very hard. But if I look at the length of the line, I know what that means. I know how big that force is. And so that was analysis, but we can actually use it for design. So here's a roof truss, and the form of the structure itself, the force diagram on the right. And you'll see that the force in this member A1 is this big. The force in member C5 is that big. So let's say you want to use one structural element for all three, for that whole rafter, that whole ridge beam. Okay, you want the same beam. Well, you have to design for the biggest force. Well, why not, instead of using this as analysis, let's use this as design. So let's use graphic statics as a design tool. Rather than have this structure, let's make it so that all of these forces in these rafter beams are equal. How do we do that? We design the forces. This is so powerful. Rather than just, how do we usually do it? We guess a structure and we do an analysis. And then if we don't like it, then we guess a new structure. Here, you can design the forces and then see what the structure is. Okay, well, obviously we got to change something else because, you can't just, you have to change the rest of the geometry to make this true. So you complete the geometry. Ta-da. You now have a structure where all of the forces in the top chord are equal. That looks a little unusual, right? Well, guess what? Maillard did it about 100 years ago, 98 years ago, down in Switzerland. He designed this so that roof beam had a constant force. And you see that in the architecture. Now, let me talk a little bit about the geometry of efficiency. Now, it's something called Mitchell trusses. Once again, I was not educated into what a Mitchell truss is. I was at a conference once in Belgium, and one of the presenters says, well, this is like a Mitchell truss. I said, well, I'm a partner, I'm a structural engineer, I'm a partner in a big firm. I don't know what a Mitchell truss is, okay? And so when I got back to the office, I had the librarian, find a paper on what a Mitchell truss was. In fact, Mitchell's original paper. And here is Mitchell. He was a engineer, mathematician. He educated in Cambridge University, but he actually practiced in Australia. And so he wrote an important paper in 1904, and here it is. It's called The Limits of Economy of Material in Frame Structures, which means trusses. And so he developed some geometries that would lead to structures of maximum stiffness or minimum volume for a given stiffness. And the first word of his paper is Maxwell, okay? And the first equation is this Maxwell load path theorem, which could be an entirely separate lecture. It's become one of my two most favorite design tools. My two most favorite design tools are virtual work and Maxwell load path theorem. When you're trying to create something on a blank piece of paper, you have to go back to physics, okay, and geometry. And so he came up with these geometric rules of how to have a maximum efficiency in a structure. And he came up with some families of permissible fields of geometries. And so the permissible geometries, he had something, which, this first one I've never found an application for. He says systems of tanvolutes, involutes derived from any evolute curve. I have to confess, I don't know what that means, okay? But basically what happens is you want all your tension members to be at the limit perpendicular to your compression members, okay? Because let's say you have some material and you want it to be equally strained, okay? That you want everything to be, all your tensile forces to be at the limit and all your compressive forces to be at the limit. And if you look at Moore's circle, that tells you they should be 90 degrees to each other. And so you end up with these fields of 90-degree curves. Another one he comes up is the logarithmic spiral. Now, what's interesting to me is geometrically, Mitchell implies that he feels that this is the most general geometry because if you, by playing with the equilateral spiral or logarithmic spiral, you can go to polar coordinates, or if you zoom in on one of the nodes, locally it looks like rectangular coordinates. If you zoom in on one of those nodes locally, it looks like rectangular coordinates. Or these things called hanky nets, which basically is saying that this cross partial derivative of the change in the angle to a reference line going in one direction and then back to the other direction is equal to 0. And this is very, very important. And it led to the following structures. These are Mitchell's trusses. These are structures of least volume. The one on the left, if you have a semi-infinite space where you can only have structure below the line, you can't have structure above the line. And if you look here, so here's a downward force, and the reaction upward. You will notice that the force in this rim, this thing that looks like half a bicycle wheel, never changes. This compression member is always orthogonal to the tension members, and all the tension members are turning the load. And so what I think nature is trying, because this is nature, this is physics, what nature is trying to tell us is that nature likes to turn loads gently. Okay? Let's look at this cantilever structure, this odd-looking cantilever structure here. Where there's a circular support here in the middle. There's a applied load out here, and you have these logarithmic spirals. And you'll notice that the force in this chord never changes all the way to the support. Nature is turning the load gently. And finally, you look at this truss on the right, which is a point load in the middle, reactions on the side. Once again, so the compression members on top. These are the tension and compression members are at 90 degrees to each other, and this compression load goes up around the quarter of the bicycle wheel, back down, and the tension member does the same. And here is the load path. By load path, I mean the force in the member times the length of the member. It's some kind of, you might say, the internal energy, if you will, assuming constant stress, of all of the members. And so this not only gives you an idea of what is a very efficient geometry, it also gives you a benchmark. No matter what you come up with, you're not going to get below those numbers. And so that's also very helpful, because a lot of times, we were talking earlier, you think, I think this is a good design, but how good is it? Well, tools like this can help you find out, how good can you be? What is the lowest you can go? He even did a torsion ball, which is really pretty hairy. I haven't done the proof on this one yet, but basically it's this kind of beach ball and torsion. So there's kind of in architecture geometry, you tend to see these three primal geometries. You tend to see orthogonal tension and compression fields, or polar, or logarithmic spirals, or combinations of those. So here is a combination of orthogonal and polar that are minimum load path structures. Now, one of the things I want to point out here, there are, in this structure, there are an infinite number of spokes. In this structure here, there's an infinite number of members in there. Well, it's pretty hard to specify that on a drawing, okay? I want an infinite number of spokes, okay? So we live in the world of discrete, and so we've been doing a lot of research into something we call discrete optimal trusses. So one of the engineers in the office, Arik Mazurik, he did this research. And so here we have this truss, which has a geometry somewhat like the Mitchell truss. And it has a certain span, x. And what we're going to do is we're going to keep it symmetrical, so we know y1 is 0. We know, these, you're not going to move these nodes. Y3 is going to be 0 because we're going to keep it symmetric. And x3, well, we fix the length. But this node can move in the X or Y direction. So we only have 3 variables to find the geometry. And remember how I said that the compression member and the tension members want to intersect at 90 degrees? Well, you know, you can do that if you have an infinite number of members, but if you have only a limited number, how's it going to work? So our first guess was that this member would bisect these two, but guess what? We were wrong, okay? And I'm going to show you his research. Look at the geometry. There's going to be some instability at the beginning because there's actually a better geometry, but at a certain point it'll stabilize, and then it will, as it goes to different lengths, look at the geometry and see if you can figure out what the rules are. There are certain geometric rules that nature is trying to tell us. Certain geometric relationships. And what Arik observed is this, that nature keeps one of the angles at 90 degrees and throws the error into the other angle. And so these offsetting angles are 2 90s, and for the geometers in the room, they add to 180 degrees, which tells you something about this quadrilateral, okay? Some very special things. And that this angle equals that angle, equals this angle, equals that angle. They were all the same. Nature is amazingly organized and regular. You just have to look for it. And I'm going to talk about this again at the end. For me, the why is much more important than the what. This tells me what the answer is, but I want to know why is that the answer? Because if I understand the why, I can do more than just knowing what the answer is. And so you can describe this geometry with only one angle and knowing the other geometric rules. That these offsetting angles have to be 90 degrees. So if I guess this angle, I know these angles, I can figure out this entire geometry. And so here is a discrete optimal truss that can be described with only one angle, okay, this angle alpha, plus the rules that the offsetting angles have to be 90 degrees. And so this is a minimum load path, 50 element truss. Inside there is another optimal structure which has only 32 members, and inside that one is an 18 member, and then a 8 member, and then a 2 member. So it's a series of nested optimal trusses, which is quite remarkable. And because of those geometric rules, it actually follows what Mitchell described. The turning angles are the same. All quads have the same turning angles, and each quad can be inscribed in a circle. Okay, that's the what. Why? Okay, we'll get to that in a minute. Now, I talked about graphic statics. Here is the form diagram, the structure on the left, and here are the forces. It's identical. For the Mitchell truss, the form and force diagram are identical. Now, you read it differently. Like the force in member A2, the line between polygon A and 2, is the length of the line A2. Those two lines are parallel. Okay? So the force in this bar is the length of this line, and guess what? If the structure on the right was the structure, the force in this bar is the length of this line. It's totally reciprocal. So we're going to come back to the moment. So you should note that every node here, like this node 2, maps to this quadrilateral that has a maximum area, okay, for those 4 bars. Now, how do we find geometry? Well, there's a lot of good tools out there that we use to help find geometry. We use programs that they're called SIMP, Solid Isotropic material with penalty functions. And these help you look for solutions. You might say the one on the upper left is where to put the members, and the one on the lower right is where to put the holes. But you can see these Mitchell trusses, these Mitchell geometries are appearing there. And we've used that on design of tall buildings, and we find this high-waisted X is more efficient than the traditional X. That it wants to be about at the three-quarter point, and this is about turning the loads gently. And there's a sweet spot where the wind comes in, it turns 30 degrees, it hits the middle, it turns another 30 degrees, it hits the far side of the building, turns another 30 degrees and goes vertically. And so, but you have to match the floor lines, but in general, this would be a 30, 60, 90 triangle. And here it is under construction. It also, we put it outside the skin of the building to keep the, and you can have more dense patterns. Here's a building that's under construction now in China, where we use this Mitchell geometry. Here's another building in China where we actually got approval, and then the client went to jail, okay? I hate it when my clients go to jail. It really screws up the project, okay? So here is, so say you're looking for ideas, and you're trying to span this thing. Well, look at here. I'm not going to build what it shows me, but it's going to give me ideas what I might build. And you can see this kind of logarithmic spiral here and this Mitchell circle, Mitchell wheel in there. There's other tools, such as the ground structures, where you have a series of nodes and you connect them to their neighbors, and then to the neighbor of the neighbors, and then to the neighbor of the neighbor of the neighbor, to the neighbor, 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 neighbor. And then you put them all together and you get rid of the ones you don't want. And so here we are, what we're doing for this load case. It gets rid of the members you don't want. Ta-da, Mitchell. He showed up. There you have. Now, this has a lot of members in it. And so what we like to do is use multiple tools and see what the ideas they give us. So we can also do the same problem with that using that polytop program. And here, it is like an ultrasound. We're growing the structure. We're moving it around until we solidify it. And you can see it's very similar to the other solution, but not the same, because the tools will give you different information. And you change the penalty function, and eventually it comes in very crisp. And so here's a design problem I was working on. And so I use this tool, and then I use this tool, and I look at them. I get a cup of coffee, get some trace paper, come up with this. Okay? Well, how good is it? Well, I can compare it to this structure, which is you're never going to build, too complicated. For the same deflection, it's within 5%. I only have 5% more material. That's pretty efficient. If I did the traditional Pratt truss, the Pratt truss has 68% more material. I've almost stopped ever using Pratt trusses anymore, okay? Because you carry the load too much. And this goes back to the load path theorem lecture I could give some other time. Okay, let's go to higher dimensions, okay? We got a two-dimensional structure. Now, it turns out, we're going to talk about something called the Aries stress function, which is related to the equilibrium of trusses. Also came to Maxwell. So here is this structure, the form diagram and the force diagram, and here are these little dashed lines. What are they? It turns out, for this to be an equilibrium, it has to be a projection, are you ready, of a plane-faced polyhedron. What? Maxwell says that hence the conditions of the possibility of reciprocity in plane figures is the same, that each figure being a perspective projection of a plane-sided polyhedron. You cannot do graphic statics unless your structure is an equilibrium, and if it's an equilibrium, it's a projection of a plane-faced polyhedron. Here's that structure we looked at earlier. I'm going to do a little trick you learned from Rankin. Put a pole out here, and I get this this funicular structure, and I move it up there, and now I have a self-stressed structure. If I know the force in one of these bars, I know the force in all the bars, and so this black truss has exactly the same force as it did before. Guess what? It is a projection of a plane-faced polyhedron. where every face is exactly flat. All the ridges are compression members, all the valleys are tension members. Exactly flat. If you have moments, then the panels won't be exactly flat. But this is purely geometry. Equilibrium is geometric in not only in 2D, but in a third dimension. And as you know, as you geometers know, every polyhedron has a reciprocal polyhedron. And if you use the Maxwell paraboloid of revolution, every face maps to a point, every point maps to a face, every edge to an edge. There is the reciprocal polyhedron, and it projects down to the forces. This is purely geometric at this incredibly complexity that these two-dimensional structures are projections of three-dimensional polyhedrons. Every face is exactly flat. So every node maps to a face, every edge maps to an edge, every face maps to a node. So what does that mean? That means that any plane face polyhedron you make, and you project the edges, all the edges, you have a structure that, you have the potential of a structure that's in equilibrium. So you could freeze that at any point, and you have a structure, an equilibrium geometry. So now I'm going to go back a little bit. Remember this annoying fact. Why? Why is that on a circle? And remember we said graphic statics, where this polygon, remember both of these are projections of plane face polyhedron. So this two-dimensional area is related to this node, and it's actually related to the Airy stress function, the polyhedron that's above that node. And Maxwell had this amazing thing where if you take the integral of the Gaussian curvature, it is equal to that area. So what does that mean? Okay, so here's a two-dimensional structure. There's the Airy stress function, and then there's the reciprocal Airy stress function that you map back down, and you map it back down here. So it turns out that this area is the integral of the Gaussian curvature of the Airy stress function. How weird is that? Okay, and so this area, this area down here, where's my cursor? This area here is a map of the angular deficit of the Airy stress function at this node. Well, this is all interesting. Well, where do we go with that? Well, it turns out that if you look at if you have your Airy stress function can have positive Gaussian curvature, it can have negative Gaussian curvature, it can have zero Gaussian curvature. Origami. Is it related to origami? Now, it turns out this is really useful, and we got this actually from Helmut, okay? So here is the equilibrium of a shell structure, okay? Where it is, a shell structure is statically determinate. I have nothing in here. This is the equilibrium equation. It has nothing to do with material properties. Here is the curvature of the roof, which is Z, and the curvature of the Airy stress function, put together in these various ways. And so it turns out for every shell structure, you have two geometries. One is the structure, and the other is the Airy stress function. And you can switch them. If this is the structure, I can look at the Airy stress function. And because I have no reverse curvature, I know that this shell is 100% in compression. Because the second derivative of this shape is always a constant number. It always has a positive Gaussian curvature. Okay? Now, if this is the structure, you can see I have a reverse curvature. So if this is the structure, I have a bunch of tension right through here. That's caused by that reverse curvature. And so here is this is the shell that was built from that Airy stress function. Pure compression. We like to play around. So we designed this one structure where we have here you see the force diagram, the form diagram, the area stress function, and the vault itself. And we played around with patterns, and we decided to build it with a robot, since we have a robot speaker later. Anyway, so we did this like 2 years ago, and then we were doing this in London, then we got hit by the coronavirus, and we had to shut down. We actually didn't quite finish the vault before we were kicked out, but we got pretty far. And so this was designed with the area stress function. And so for every roof, this roof, if it were, I think you got bending here, so whatever. But if this were a pure axial roof, there would be 2 mathematical functions for this roof. And that'd be a good master's thesis. So like, calculate the area stress function for this room. One is the structure, and the other is the area stress function. And you can choose which one you wish. So one of these is the roof. You choose. The other one is the area stress function. And the forces, let's say this is the roof. See how there's a big angle change right here. That means there's a big compression thrust right here, because they map to each other. The one diagram tells you the forces in the other. If this were the structure on the right, you can see that the forces would be very, very smooth. Okay? And so what we do is, we play around, we guess a shape, and then we look at the area stress function. If somebody shows you this shape, you say, well, I guess it's okay. Then you look at the area stress function and say, well, that's not really very good, is it? I mean, and you can see it with your eyes. You don't have to look at it. Is that blue-green? So you guess something else. Well, that's a little bit better, maybe. Okay. And then we go to the mathematics of Chris Williams, and we look at electromagnetic theory and come up with a geometry. And look at this one. So this is this is the roof, and that's the area stress function. Much smoother, much happier structure. And then we decided to put those 2 on a date. And so A and B went on a date, and they had C, okay? And it turns out C is a self-area. It is not only the structure, it's the area stress function. It's both. Okay? And here's the force diagram. Guess what? Every one of these quads has exactly the same area because it has constant isotropic curvature. And every octagon here has exactly the same area as every other octagon in this force diagram. Unbelievable. Okay, then, got to bring it back here, right? Strubecker, okay? Anyway, so, by the way, if somebody wants to translate his work into English, I would really appreciate it, okay? All of his work is in German, okay? So you cannot read about isotropic geometry in English because it doesn't exist, okay? And so, we were looking for a constant isotropic curvature roof shell, and so helmet pointed is this one because we wanted something that was irregular. This is a self-area. This is both the structure and the area stress function. Quite remarkable. Here's one of my favorite structures in the world, which I had absolutely nothing to do with. I had nothing to do with it. It was done by Fosters and Partners, Burl Hopple, local boys, Wagner Burl. I'm sure most of the work was done here in Vienna on this one. And then Professor Chris Williams, a brilliant mathematician, engineer, who sponsored that conference not too long ago. And so here's the grid shell. Here's the area stress function, and here's the force diagram for that roof. So you could actually design that roof purely with geometry, only geometry, no finite element programs. Okay, I'm going to quickly go to higher dimensions because I'm running out of time here. What about three-dimensional structures? Well, we're going to go to Rankine, okay? And by the way, the title of my speech was ripped off from Rankine because when he got his Regis chair at Glasgow, he said, on the harmony of theory and practice, or something like that. And so that was the inspiration for my title today. And this is his entire paper. Okay, I know of 2 PhD theses that have been done on this paper. It is 3 paragraphs, 4 sentences. Okay? He wrote it in January and it was published in February in the Royal Society, okay? And he goes from 3 dimensions to 4 dimensions, where every node maps to a cell or a polyhedron, every edge to a face, which is perpendicular. The edge is perpendicular to the face, and so on. And so what you have is you have this reciprocity. One is the structure, the other is the forces, okay? Where every node maps to a cell or a volume, and every face maps to a line which is perpendicular to the face. And so the force in that bar is equal to the area of that face. And so 3D graphic statics. And so, there's research, Masood from the University of Pennsylvania is doing these research where you take like a polyhedron and you subdivide it and you create these equilibrium geometries. Ta-da. Okay, that's from a 4-dimensional polyhedron. Here's another example. This is the work of Alan McRovey up at Cambridge, where he takes the Maxwell form and force diagram, and then he throws on them an Airy stress function, and then he does he does what's called coning, where you take a point and you drag it down, and from that he's able to create an equilibrium roof structure where every face is exactly flat. Here's another example. Structure, not one finite element program is used. Totally done with only geometry, the geometry of equilibrium. You can also use geometry for mechanisms, static kinetic duality. Both of these are projections of a plane face polyhedron. If I move that node C on the right up and down, if I move this node C up and down, what it does, it stretches, it's parallel redrawing, which it turns out if you rotate that 90 degrees, that's the mechanism. There's the relationship between equilibrium and mechanisms. Okay, I'm running over too much. Okay, so here we go. I'm to the end here. This is to the architects, engineers in the room, and the geometers. Why is more important than what? You can get an answer, but why is it the answer? I think geometry will help us understand the why. Why is it the answer? Now, as an engineer, I was taught like next to nothing in geometry, okay? Of course, you had calculus, and maybe you had differential geometry or something. But basically, I was never taught about projective geometry. These are some books from my library, because I had to teach myself. The most useful is actually Cremona, because he drew lots of pictures, okay? I'm an engineer. I need diagrams. I need lots and lots of pictures, okay? Next most helpful is Klein, okay? Because he kind of brings it a little bit to the modern era. Coxeter is good, but it's written for you guys. It's not written for me, okay? It's not written for an engineer. And then when I read Maxwell, I try to figure out what the heck, where did he get that? I always look to Euclid, because back then, everyone had to memorize all Euclid. And so there you had it. So can architects and engineers get together, can we get our street lights closer to each other so that I can see what you see and you can see what I see? With that, thank you.
Thank you so much. Thank you so much for this great speech and advertising so much for geometry, of course. I like it a lot. Are there any questions? Quick questions, we're a bit above.
Yeah, and I'll be at the coffee break, so,
right.
Yeah.
Okay, so maybe we move the questions. Here's one, right? Okay.
Hello, thank you for the presentation. It's just a short notice rather than a question. I'm familiar with the research of Philipp Bloch, I think at ATH Zurich. Do you know that? And your presentation reminded me of that. So he's working on making slabs lighter, and the forms that you showed resemble those, because I know his work from Instagram and haven't met him unfortunately yet. But is it, do you work together? Is it something similar?
Yeah, I'm a great admirer of his Bloch group. Masood, the guy from University of Pennsylvania, he got his PhD from Philipp Bloch, and so he's doing a lot of research in this common field. He's more on the pure compression structures. I'm okay with tension also. He lives, but what he's done is really brilliant. he kind of tied one hand behind his back. He says, I'm not going to use tension. I'm going to limit myself just to compression and see where that takes me. Felix Candela only did high pars, okay? He could have done other mathematics, but he tied his hand behind his back. He said, I'm going to go deep into this one area. And Philippe, we actually do collaborate. I was on Masoud's PhD committee, and so we do overlap a lot with Philippe Bloch and the group there in Zurich.
Okay, let's leave it with that, and thank you very much again for this great presentation.